This everybody can see, right?
Yes.
Yeah. Okay. Okay, now can you share your screen?
Showman, you're still sharing your screen.
Yeah, I'll stop sharing. Yeah.
Yeah, you have stopped sharing.
Yeah. Professor Lang, can you start sharing your screen?
Should I start it? Okay.
Yeah. Just share it.
Yes, I did.
Yeah, it has come. Can you just go a couple of slides just to check? Just move ahead by a couple of slides. Yeah, perfect. Okay.
So I say stop share.
Yeah. Right.
And should I say start video? Yes.
Right. Okay. So I'll just.
Showman,
Yeah.
I'm not going to start my video because of bandwidth problems.
Yeah. So. Yeah. So, Vedanga, I guess it's better to keep the videos short, or what's the bandwidth thing like?
I mean, for us, it's fine.
Okay, so we leave it to the
Maybe
speakers.
one, okay, Sourendu has issues, but if others while speaking can have it on, then.
Acha, okay. So we can do that. So let us say when you are somebody is speaking, they keep their videos on. Otherwise, they keep it off. Okay.
Okay.
Yeah.
Okay.
Okay.
Okay. So we have, I guess, a few minutes before we start. I have just prepared one slide to start it, showing a couple of photos of Pushan, and then Professor Haridas, and then in the visual order. Yeah, and what will we do about questions we take after the talk, or in case somebody has a physics question? Vedang?
Yeah, up to you, Somen. I mean.
Okay, so we'll say ask people to write the question in the chat box, then I decide.
Yeah.
Okay, fine. Okay. So let me start this session in memory of Pushan Majumdar. I think I'm speaking for many in the audience when I say that the news of Pushan's passing away, I mean, hit us like, even in the strange times that was this May, it hit us like a ton of brick. Not only because he was so young with so much of life and physics ahead of him, but also because, I mean, physically he seemed so strong and active. I mean, whose idea of a relaxing week was probably, going up 4,000 meters in the mountains and walking a few hundred kilometers. So, this year was a difficult one, but this DAE Symposium gave us an opportunity to look back at the physics, some of the physics that Pushan has done, and share some of the memories of the person and all that. So Pushan's physics institutional chronology goes somewhat like this. His undergrad in presidency, then PhD in IMSc, then he did postdocs of various durations in TIFR, in Munich, then in Graz, and in Münster. And then he joined IACS as a faculty member, and here you see him with some of his IACS colleagues. So he's primarily a QCD person, using numerical lattice tools to study non-perturbative QCD. He also had interests in and has worked in formal problems in mathematical physics and recently some condensed matter problems. But today we'll hear talks about spanning some of his, or most of his work in lattice QCD. We'll have Professor Haridas, who has seen him in IMSc and later, and Professor Christian Lang, who was his postdoc mentor in Graz, and Professor Sourendu Gupta from TIFR, who has worked with him almost till the end. So we'll start the session with Professor Haridas. As always, I request you to keep your microphones muted if you are not speaking. Oh yeah, and at the end of the third talk, we'll have some time where you can just unmute your microphone and share your memories of Pushan or whoever in the audience wants. So during the talks, we'll take questions in the end. So if you have any question, please write it in the chat box. And of course, when you are not speaking, keep your microphones muted. Thank you.
So should I start, someone?
Yes, please.
Okay. Good afternoon, everybody. I hope you can hear me. Today is both a very sad day for me as well as a happy day. It is sad because we have lost a friend, collaborator, and a very active and creative person in Pushan. At the same time, I'm glad that the community, is organizing this memorial for him, showing their appreciation for many things that he has done for lattice gate theories. So with those few words, let me start. I'll be mainly talking about the joint work with Pushan and me did, around 2004 to 2007, unraveling the QCD string. And of course, he contributed much more than what I'll be specifically talking about today, even with regard to QCD strings. He did some very interesting work with Sebastian Brandt on the spectrum and so on. With the Japanese couple, he had also done a lot of work on U1. I will not be touching on those. Time is short and I will simply, present the work that we did together. So with that, let me start. So this is what I'm going to talk about. A little bit of pun, pushing the QCD strings frontier, also pushaning the QCD strings frontier for me because, you know, okay. Yeah. So this is, I've known Pushan for a long time since he joined IMSC, and here is a picture of him as a graduate student in IMSC around 1996. This is a picture taken immediately after he got married with his wife Basudha, and there you see, you know, Professor Jagannathan from IMSC and Professor Gunther van Galen from Bonn. You know, we all used to meet often and have interesting social meetings. Pushan was also an adventurer to the core, not just in his works in academia, but, you know, he loved mountain climbing. And this is a picture of the sunrise in Kanchenjunga, which he sent me. So that is just a small glimpse into his personality. In the academic front also, he was very adventurous, because when he came to IMSC, he did not just do the standard coursework and do whatever his thesis advisor asked him to. He, you know, worked on several very deep and interesting ideas and topics, and some of them very formal, very important for, you know, quantum field theories in general, like gauge field copies, duality transformations, monopoles. And interestingly, with Sharat Chandra, his advisor, he also did a very interesting piece of work on coherent states of the hydrogen atom. So this shows his very broad interests and depths and technical ability. He also had a taste for highly mathematical topics. With Elizabeth Gasperim, you know, he looked at BPS counting, instantons, and holomorphic Euler characteristics, and so on. So anyway, let me come back to our topic today. And relativistic strings were proposed in 1970 when the meson field theories had failed rather miserably in accounting for strong interactions. And that was a time when no relativistic quantum field theory showed any promise of explaining, you know, some highly intriguing data. First, S-matrix theory was proposed by Chu, and then one thing led to another, and it culminated in the concept of relativistic strings, proposed simultaneously by Holger Nielsen, Nambu, and Susskind. You know, what they basically showed was that a relativistic string could reproduce both the Regge trajectories and the Veneziano amplitude, which was in some sense the milestone of all the earlier work. But this idea ran into difficulties very quickly, requiring space-time dimensions to be 26. Rather remarkably, at the same time, quantum chromodynamics was proposed as the underlying quantum field theory of strong interactions. And to date, there is enormous evidence that it is the correct theory. One remark is that the only person who had a foot in both the camps was Gell-Mann, you know, who was one of the creators of quantum chromodynamics. And he was also the one who convinced Chu that S matrices have various analyticity properties, and that could be the start for building a description of strong interactions. Major unsolved problem to this quantum field theory was quark confinement, and here is a cartoon of this, that quarks were never seen freely, no matter how high the energies were. So for some reason, it was as if they were confined permanently. But how a field theory could ever achieve such a confinement, absolute confinement, permanent confinement, was not at all clear. So the breakthrough in this was the idea of QCD vacuum as a dual superconductor. In a superconducting ground state, the magnetic flux would be squeezed into a very thin flux tube. So if you now took a monopole and an anti-monopole connected through this flux tube, then its energy will grow linearly with distance, and it would realize confinement. But the question is QCD vacuum such a superconductor? And in particular, it has to be a dual superconductor, because in QCD, it's a color electric charge that we want confined, and therefore, electric and magnetic aspects have to be interchanged. Now, flux tubes can be investigated in lattice gauge theory by studying either very large Wilson loops or Polyakov loop correlators. The central object is the static quark-antiquark potential, and that can be parameterized in this fashion. First term signals confinement, and all the others are sub-leading terms. On rather general grounds, Luscher and others had shown that the first coefficient A is completely universal. It doesn't depend upon the gauge group representations of the quarks, nothing. It only depends on the distance, and this is called the Luscher term. And rather general grounds, you can also show that B is 0. A convenient quantity is not V of R itself, because the magnitude of the confining term is so big that it completely swamps all the others. Therefore, you form the C of R, which is a scaled double derivative, and that removes the first term completely, and the second term will just give a constant. So deviations of this from constancy will shed light on all the other terms. Now, numerical studies were undertaken by Luscher-Weisz. A breakthrough was an amazing algorithm by Luscher-Weisz called multi-level, and Pushan was one of the leading experts in the world on the applications and understanding of this multi-level algorithm. With this, the A term, called the Luscher term, could be estimated to about 15% accuracy by Luscher-Weisz around 2000. And I have also shown a slide showing the results for three-dimensional theories and four-dimensional theory, and the horizontal lines are the constant value A, as the separation becomes very large. Because of resources, Luscher-Weisz had to stop short, and unfortunately they stopped short of exploring the most critical region. As a result, nothing concrete could be said about the string, except that it is very likely a bosonic string because of the numerical magnitude of the Luscher term. Now comes the work that I did with Pushan. In 2004, as part of the 10th plan, as well as the objective of an alliance of Indian lattice gauge theories, which in the current political climate, you could call it LGT Gatabandhan, I built a teraflop Linux cluster called Kabru. It was on the top 500 supercomputers twice in a row. I was looking at a worthy problem to put Kabru to work. And Pushan, by the time, had become an expert on multi-level, and as I already mentioned, had applied it to a number of interesting and fundamental problems. So I decided with him that we will dedicate Kabru for a very thorough study of flux tubes in 3 and 4 dimensions with SU2 and SU3. And the special design features of Kabru allowed us to handle much bigger lattices, and we could achieve significantly higher accuracies and probe much larger QQ bar separations. And this led to us probing an extremely interesting region of the quark-antiquark potential. Just to impress you on the difficulties, increasing the separation by even a single lattice spacing required huge increases in numerical resources. So here I show the results for 3-dimensional SU2 on the left and 4-dimensional SU3 on the right. The small distance curves are derived from asymptotic freedom to whatever loop order that you want. In 3 dimensions, beyond one loop, the theory is infrared divergent, and therefore you cannot really compute this in perturbation theory. And the right-hand curve is what would come from the bosonic string theories. I'll explain it in a little bit in a few minutes. And you see that our data beautifully interpolates between the asymptotic freedom and the string regime. In the 3-dimensional case, the data is so accurate that you can even calculate the infrared counter terms needed for a complete description of the, the static potential. And in 3 dimensions, we also see, continuum limit has been reached because different lattice spacings all sit on top of other. On 4 dimensions, we could not probe too many lattice spacings because of numerical limitations. But with what we did, you again see interpolation between the asymptotic freedom end and what I called RVs, which is the exact potential coming from bosonic string theory. The exact potential that I mentioned is given here. And this is from a bosonic string theory in capital T dimensions, with sigma being the string tension, which is the coefficient of the Nambu-Goto action. For large R, this has the following term. The first term is the confining term. The second term is completely universal. Even though it's 1 over R, it is not a Coulomb potential. And according to this bosonic string theory, even the 1 over R cube term is universal. It doesn't depend upon the gauge group. It only depends on the dimensions, nor on the representations of the quarks. 1 over R squared term is exactly absent. I don't have the time to completely explain that to you. What our studies indicated was, to a very high degree, flux tubes actually behaved like fundamental strings. But bosonic strings were consistent only in 26 dimensions, but QCD is a consistent theory in 3-4 dimensions. Is it a numerical accident? That is extremely unlikely. And what resolved this was an idea of Polchinski and Strominger, motivated by Polyakov's subcritical string theories. So they suggested modifying the string action by an additional term, and the coefficient beta is allowed to vary, and by requiring the anomaly to be absent, beta is fixed. Then these string theories, which are effective string theories, are consistent in all dimensions, and we could apply them to quark-antiquark potential and show that our results actually is not just a numerical accident, that they are actually valid in all dimensions. But this action is sick for many configurations, but remains sensible for small fluctuations around a straight confining string. It can be used as an effective theory. All the actions are conformal invariant. So what I did later on was, with Peter Matlock, I proved that 1 over R cube, the spectrum of these effective theories is the same as that of the bosonic string theory. And then with Peter, I developed a covariant calculus with which you can construct effective string theories to arbitrary order. And with Peter and my ex-student Yashas, we proved a number of results, which I don't want to take up the time to describe, but those interested can see my QCHS conference talk. Here is a short bibliography. First 2 are papers with Peter. Next one is where we showed the 1 over R cube term is indeed that of the bosonic string theory, and it is not some numerical accident. And the third is the covariant calculus. Very beautiful results were obtained with Peter. Last is the AIP conference reference. Thank you very much, and I will stop here.
Thank you, Professor Haridas.
I hope I didn't take too much time, Saman.
No, that was fine. Okay, so can you now stop sharing and we?
Yeah.
Okay. Professor Lang?
Yeah, I'm just fighting with the computer. Wait a second.
Okay.
Yeah, but
Can you see something?
Yes, we see your screen. You want to make it full screen? Yeah. Thanks.
Okay. Should I start?
Yes, please.
Yeah, Pushan was in Graz, as was mentioned already, in 2003 to 2005. And he was there on a Lise Meitner fellowship, which is quite prestigious. It's not the standard postdoc fellowship. It's a special one where you have to get a little bit more money, which is good. And you have to write a proposal, a real project proposal, and this goes to a committee. And so finally he got it, and he spent his 2 years in Graz after his work in Munich, where he was doing strings, as we learned. Now in that time, somehow it doesn't work. Okay. Yeah. At the time, we had a small group there, and you see on the photo, for instance, Stefano Capitani next to Pushan and Leonid Glossman and myself and two doctoral students. One of them on the right-hand side was a collaborator of Pushan in several projects. This is a small meeting of the local group, which we do once or twice a year in the southern part of Styria, which is a vineyard area, so it's quite pleasant there, and we have something to eat and drink and discuss and have fun. And Pushan was with us at that time. Okay. I listed here the publications with Pushan, which I had joined with Pushan at this time, essentially. And you see Wolfgang Gortner is always there. He was the doctoral student. And you also see there are two topics which come again and again in all these titles. That's dynamical quarks, and that's chiral improvement. And that was at the heart of the issue at this time of the development of QCD, because dynamical quarks means to have a full QCD with dynamical fermions in a vacuum, and chiral improved is a special property of the quarks, which I will talk about in a second. I have to go forward somehow, it doesn't work. So, okay. Let me first talk about dynamical quarks and the issue of dynamical quarks. In QCD, you have the main object you calculate is a correlation function. In this case, it's a correlation function of two hadronic operators, which are created in Euclidean time at time 0 and destroyed at time t. And from the behavior of these correlation functions, you learn about the masses and the wave function properties of these hadronic objects, ab initio, so to say. Ab initio means that you have to solve a functional integral, which is an integral over the gauge fields u, and over the Grassmann variables psi and psi bar. And the Boltzmann factor is the gauge action, and the psi d psi fermionic action, the Dirac operator essentially, multiplying with these hadronic objects there. Now, the gauge fields are bosonic variables, and they can be treated well with Monte Carlo calculations on lattice calculations, whereas the psi psi bar are Grassmann variables, and they don't have a simple representation on the computer. So what you have to do, you have to integrate out the Grassmann variables. And what you get is then that once you integrate it out psi and psi bar, you get factors which are the determinant of the Dirac operator for each quark one determinant. And the hadron operator's propagation is written down in terms of propagators for the quarks. So in this example here, you have U quarks and D quarks, so you have both determinants, and you have products of d to the minus 1 of the U and D quarks, depending how many quarks are in the operator. If there are mesons, for instance, there would be 2 quark propagators, of course. Now, what you do is, if you put it on a lattice, this becomes an approximate sum. It's approximated by Monte Carlo sum over gauge configurations with the corresponding weight factor of the gauge configurations, but then you have to multiply with the determinants and the inverse Dirac operators. Now, physically, the determinant represents the C quarks, and the d to the minus 1, the propagator of the quarks, are the valence quarks. And at the beginning of, in the first years of QCD, it was hopeless, but around the turn of the century, people started to introduce C quarks in calculations, and not just valence quarks. However, until that time, one had quenched approximations, so one neglected the determinant, which means that you see essentially propagation of quarks in a gluonic, full gluing medium, but you don't see the C. In order to see the C, you have to introduce the determinant again, and this little part of this femto universe then really is with dynamical quarks. So it's full QCD, as people say. The question is how to introduce the determinant as a weight factor, and the method of choice at that time was, or still is, the so-called hybrid Monte Carlo method. That's a combination of a molecular dynamics differential equation type of development with Monte Carlo steps every now and then to get the correct weight measure. Now this is quite complicated because in the evaluation, the microcanonic evaluation of this molecular dynamics behavior, you have again to calculate very many times the inverse of the Dirac operator. And so it's quite demanding. Oops. And this was a task, which is a task which Pushan took over, and I will come back to that in a second. Before let me briefly remind you on the second aspect of QCD, that is chiral symmetry. Chiral symmetry means a special symmetry of the massless QCD action. So if the QCD Dirac operator, if you look at the action and have no mass in the quarks, then you have a so-called chiral symmetry. If there are two quarks, two-like quarks, then it's SU2 left times SU2 right. Now, if you switch in the complete QCD, the interaction, the gluonic interaction in particular of QCD, then you find out that the symmetry spontaneously breaks. It's no longer there, and you get a non-vanishing expectation value of the condensator psi bar, which would be vanishing if it's not broken. Now, there's a theorem by Banks and Kasher, which relates this breaking of the chiral symmetry with the appearance of a boson, which actually is the Goldstone theorem formally. Whenever you have a spontaneous breaking of such a symmetry, you have massless bosons, so-called Goldstone bosons. In our case, it's the pions, because the bosons here have the quantum numbers of the pion. Now, the pions are not massless, but also the quarks are not massless. They're close to massless, they're very light, and therefore the pion is light. It's the lightest hadronic particle we know. So what one would like to see in a computer simulation, or in computer calculation, I should better say, is one would like to see the pion to occur. One would like to see, if you start with massless QCD operators, that you get spontaneous breaking and you can get a pion with a certain behavior, which is predictable. Now, that would be nice if the Wilson action, which was originally proposed, has chiral symmetry, but it has not chiral symmetry. It breaks chiral symmetry explicitly. So putting QCD on the lattice breaks chiral symmetry if you do it in the way Wilson does it. Wilson's action is quite simple to simulate. It has 8 nearest neighbors, essentially, which are taken into account. So it's 8 terms for each side, but it violates chiral symmetry explicitly, and therefore it's hard to see how the spontaneous breaking occurs on top of that. There was an action at that time already around 2000 that is chiral symmetric. That's the so-called overlap action, suggested and discussed, for instance, by Neuberger and others. That overlap action is chiral symmetric and would be a nice candidate. And actually nowadays it's used, but at that time it was much, much too complicated. It is quite expensive. It has to be approximated. Essentially, it amounts to getting the sign function of the Dirac operator, and that has to be done by eigenvalue decomposition and very complicated methods, which led to a factor of 100 or 500 in effort. So it was unfeasible at that time. Now, we had at hand at this time a so-called chiral improved action. Christoph Gatringer was suggesting that earlier, and we had already some calculations in the quenched approximation. Now, this chiral improved action was, as the name says, chirally improved. It was not perfect, but it was better than Wilson. It was less good than overlap, but it was a finite number of terms. It was a high finite number of terms. It was 2,000 terms, over 2,000 terms for each side. So it's like having 2,000 neighbors. So it's looked impossible to do it, but in quenched we could do it. And Pushan undertook it to implement the hybrid Monte Carlo algorithm in a technically highly demanding work together with Wolfgang Gordner, and implement the CI, the chiral improved action, with this hybrid and Monte Carlo algorithm, and get constructed a set of programs to compute gauge configurations with these dynamically fermions of the CI type. Now, having these gauge configurations, this is essentially the basis, like in all QCD fermion calculations, it's the basis for many, many subsequent projects. Pushan himself did eigenspectrum of the Dirac operator and looked at the QCD condensate, which you can learn from the eigenspectrum. Hadron masses were calculated. This is then used by other authors, hadron structure, and also excited states, which is one of the basic, still one of the big problems in hadron spectroscopy. So it was quite a lot of work, and Pushan successfully did it. And if I look at the publication list, I selected the highest cited papers of Pushan and indicated which ones are QCD, which one are strings. You see it's almost equally distributed. There are almost as many papers about strings as about QCD. And I also indicated in red the papers written in class. So this belonged to the top 10 list of Pushan, essentially. So it was quite successful, and did not look at how many papers used them, but you can see from the citation that at least 37 or 33 papers, other papers used the basis provided by Pushan. I'm coming to the end. I'm not using all of my time, it seems. Pushan was quite impressive. I copy on the last transparency I cite my own reference report, which he asked by applying for positions in 2007, and let me quote it. So that's a reference letter in 2007, in which I said Pushan was a driving force and most active contributor. I consider him an experienced theoretical physicist, excellent analytical understanding, leading recent research activities in dynamically chiral fermions. He's highly qualified, and although he's an easy talk to personality, it's open-minded and very friendly. This picture, this photo, which I found in recent days, actually is from a workshop in ECT Trento in Italy. And he is up in the mountains, which he liked very much. I remember, as Harry said already, I remember many photos from mountain hikes he undertook. Usually he sent me a Christmas card or a Christmas mail, I should say, with one of these photos looking on a lake somewhere in the mountains or at some mountain tops. I do miss him. Okay, thank you.
Thank you, Professor Lang, for this excellent talk, especially this excellent quote in the end. So, Sourendu, can you unshare? Yeah, can you stop sharing? Yeah.
So Sourendu is next, right?
Sourendu, you may be muted.
That's right. Yeah. I'm trying to share, but I don't see it on my screen. Okay, let me try it again. Yeah, there it is. Yeah. Okay. Can you see it?
Yes. Yes.
Okay. Great. So, given that other people have spoken about various other parts of Pushan's physics career, I thought I would confine myself to his years in IACS. But of course, it's not about his work in IACS. He was working with many of us across the country and abroad.
Sourendu, can you make it full screen?
and I'll talk about all of these. So Pushan's first paper I checked was written 13 years after mine. Okay, so that means Pushan right now was at an age where you're at the peak of your career. You do your best work at the age that he was in. And of course, we'll now never know how he would have done. But one indication that he was on top of things is the number of unfinished projects that he had. With me personally, he had 3 unfinished projects. And I know that several other people had unfinished projects with him. Maybe they're here, maybe they'll talk about it later. Okay. If I look at what his major activity during this time, these 12 years, then I would think that the first thing I would say is that he was an extremely valuable member of the Indian Lattice Gauge Theory Initiative, something that Haridas already talked about as the Lattice Mahagathbandhan. He was also an expert on new computer architectures, and that played a big role in what he did in ISCS, how important he was to ISS. He was also a member of the National Supercomputing Mission for one of the committees for a short while. And of course, he played a major role in the acquisitions that we made for the ILGTI, the Lattice Gauge Theory Initiative. And of course, he had great expertise in quantum field theory. So that led to lots of other collaborations. It meant that he taught a lot in ISCS and also in nationwide schools. The
Circ schools.
DST, yeah, the DST schools and Circ schools. Thank you. And of course, he had expertise on other things. I mean, in general physics and numerical methods, which he was always open to discussing. So I made a list of his collaborators during these 12 years, and you can see here that there are like about 20 collaborators I can list here. Okay, many of them were lattice gauge theory, core lattice gauge theory research papers were co-written with some of these people. Okay, but you can also see names like Elizabeth Gasparim and Kaushik Ray, with whom he collaborated on mathematical physics papers, a BPS counting paper. Okay, then you can also see Arnab Sen, with whom he had some unfinished work, which I think Arnab is still carrying on and he'll finish it at some point. Okay, he wrote a Scholarpedia article with Peter Weiss. So there were a lot of things that he did at this time. Okay, I just gave you this list of collaborators to show you what kind of a breadth he had, what a central position he occupied in collaborations within Indian lattice gauge theory community and outside of that. So what I decided to do, I can't speak about all of this. So what I decided to do is to take two of the two best cited papers during this period and tell you briefly what his contribution, what those papers contain and what his contribution to them was. Okay, so the first paper, the most well-cited paper actually of his whole career, is on heavy quark momentum diffusion, okay, in heavy ion collisions. And this was written along with Debashish Banerjee, Soumen Datta, and Rajiv Gavai. Okay, the problem that they tackle is the following, that if you look at perturbation theory results for the diffusion constant of momentum diffusion constant of heavy quarks, that's D, okay, then and you try to compare it with experimental results, which is down here, then you see that there's a huge difference between them. Remember, this is only 1/4 of the perturbative result. In this figure, the authors have divided by 4 to bring it within this range. Okay, so the real thing would be way up there. Okay, so there was this huge discrepancy between what QCD seemed to predict and what experiments saw. So these people thought that they should really look at it, look at the problem non-perturbatively using the lattice. And their result was seminal, absolutely outstanding. They found results within a certain approximation I'll tell you about, which agreed fairly well with the data. The x-axis is actually a temperature scale, and it's in units of Tc, the QCD scale, so to say, temperature scale. Okay, and it's a fairly flat diffusion constant. Okay, agreeing pretty well with the experimental result. And this changed completely the language in which people talked about heavy quark diffusion. Okay, it was earlier thought that because the quarks are heavy, therefore weak coupling theory would be enough, but it was clear after this calculation that it's terribly non-perturbative. People have gone on to improve the calculation, but theirs was definitely the first, and it's widely recognized as such. So technically, what this involved was a calculation of electric field operators, the correlation function of electric field operators, color electric field operators at 2 points, separated by a Euclidean time-like distance. Okay, why Euclidean time-like distance? Because all these calculations at finite temperature are done on a Euclidean lattice, and to make contact with real-time transport phenomena like diffusion, you have to do an analytic continuation to real time. Okay. Now that analytic continuation is extremely complex calculation. Okay. And of course, it won't work unless you can get the errors in the Euclidean calculation down to really small values. Okay. Because it's a ill it's not a very well constrained process, so those errors tend to blow up when you do analytic continuation. So the Euclidean calculation has to be done with very small errors. Okay, and that was actually a specialty of Pushan. So this is the expertise that Pushan brought into this game. So this calculation was done in the quenched approximation of lattice QCD, which means that the fermion loops were not taken into account. Fermions were there only as test particles, the heavy quarks in this case. Okay, and here's a fermion propagator, which you build out of gauge links. Okay, each of these lines is a gauge link on the lattice. Okay, and a static quark placed here can be represented in some way by these gauge links, a path of gauge links, which goes from time 0 to time 1 by temperature, and using the boundary conditions, it winds back. But then this is dressed by these electric field operators. Now, in order to evaluate this operator with little error, what they did was something known as multi-level algorithm, in which they divided up the lattice into 4 pieces that you can see here. 1, 2, 3, 4. This is just an illustration. You can divide it up in many ways. Okay. And what they would do is to do integration over this part of the lattice and this part of the lattice, okay, with very high precision, and then use that to get the use that information to put it into the calculation in these 2 sublattices. Okay, by dividing the problem into multiple pieces, they could actually make a lot of progress. Okay, so this is typical of many kinds of computer algorithms. If you divide the problem into smaller pieces and solve the smaller pieces, and then you're able to put it together well, then you get a tremendous numerical advantage. Okay, so this was the kind of thing that Pushan brought into this game. Okay, and without this seminal result would not have been possible. So that's one. And the other thing I picked up was the second highest cited paper in this period. And that was a paper that he wrote with me on the equation of state of QCD. Now, you might wonder what's new about the equations of state of QCD. You've probably heard about papers from the 1980s about the equation of state of QCD. So what's new here is that we looked at the equation of state at finite baryon chemical potential. Now, this is a technique that we developed in Bombay. Actually, Pushan was involved in the first calculations in his postdoc years in TIFR. And then when Pushan came back, he was very much a part of this ongoing project. Okay, so this was a time when our big computers in ILGTI were busy doing zero temperature calculations. So we didn't have any big computers. And then we involved Pushan to move these really elaborate calculations into small computers. And that's exactly the kind of thing that Pushan loved to do. He took these fermion algorithms, okay, these fermion measurements of the equation of state, and moved them into a cluster. And it was so well done that we could finish this calculation in about 3 months. Okay, that's unthinkable on small machines usually. The results were spectacular. We could get the equation of state with very low errors. So here I show you one physics result, which is the compressibility of QCD matter. Okay, and the bulk compressibility of QCD matter, bulk isothermal compressibility of QCD matter, that's undefined when the chemical potential is 0. And you can understand why. If you think of say black body, a photon gas, okay, then it has a pressure, but the number of particles adjusts itself when you change the volume. Okay, if you take the black body and you make it larger, then the number of photons that are emitted, the number of photons in the cavity become larger. Okay, if you make it smaller, then the number of photons adjusts itself again to keep up that constant pressure. So when you take a photon gas, there's no bulk compressibility. And similarly for a pure gluon gas. So you need some number of fermions in the gas in order to give you a compressibility. And that for the first time we could access because of Pushan's enormous contribution to this project. I could tell you about many other things, but I think this kind of gives you the flavor and it ties in with the previous 2 talks. Pushan had 2 major pieces of expertise. One was fermion algorithms, another was those noise reduction methods for glue sector observables. And he could use them, he could leverage them to be a central part of almost every calculation that we did for a while in the lattice gauge theory community. So he will be really badly missed. His expertise, his ideas will be badly missed in this community. Okay, but you know that a person's contributions are not just in his papers. Okay, Pushan had many other contributions to his department. And when I talked to his colleagues, they mentioned many, many different things. One thing that I know for certain was this thing that he's holding there. He's standing there with a cup of coffee. He used to run a wonderful coffee club for his department. This was one of his smallest achievements. He had an espresso machine and he would pull it out for a coffee whenever people wanted. But apart from that, he was responsible for the whole computing infrastructure of IACS, the numerical computations part. He was instrumental in getting the first supercomputers. He was instrumental in setting up their cluster systems. Okay, so he was an indispensable man for the whole institute, not just for the department. I believe he was very well liked by students. I'm told that students knew him as a no-nonsense person, but a friendly no-nonsense person. And that what they liked was the fact, that's little remarked in Teacher, that when he presented a calculation on the board, he would get all the factors. He would have worked on it. He would get all the factors right on the blackboard. And you could do a one-loop calculation on the blackboard. You could sit through a lecture by him on a one-loop calculation, and the final result, it would just be the textbook result. I think students liked that meticulousness with which he presented things. So, of course, he taught also, as I said, in the nationwide schools, the SCRC schools, and he did a very good job there too. But as everyone has remarked, he was a climber. He loved the mountains, and here you see him with a cup of coffee on a lake, by a lake, the Gurudongmar Lake. It's at 5.4 kilometers height. And I remember when I went up to that lake separately, I was feeling the lack of oxygen. And I have photographs which I can't remember taking, but Pushan seems okay. It's, he was a very good climber, and it was quite a shock when I heard about him having a heart attack. I had just talked to him on a Friday, and we were planning to spend the next week finishing off certain things and then thinking about whether there was a paper we could write up. And on Monday night, I got this call from his friends, and it turned out that he had gone home and had his dinner, and he had a heart attack and he died. He leaves behind a family, his wife, 2 young children. And I think they'll miss him much more than we do. Thank you.
Thank you, Sourendu.
Yeah.
I think, I keep solace in what Professor Lang ended with. We can think of the memories more than the loss. So I do not see any questions. So if it is okay with everybody, I will open this session for comments from others. In particular, okay, there is something from the, okay, yeah. Indumuti thanks Sourendu for the personal photo and the general personal touch of the talk. Professor Weisz, his mentor in Munich, and also, as Professor Haridas said, the brain behind the multi-level algorithm which Pushan became an expert in, is in the audience, I can see. And he had actually sent a message, something which we can read if he is not there. But Professor Weisz, would you instead like to say something yourself? Is everybody unmuted now? The volunteers, can everybody be unmuted? Can they unmute themselves?
Yes, they can.
Okay. Sir, would you like to say something yourself, or do you want us to read your message, Professor Weisz? Okay,
I don't see him in the list, so maybe you can read it.
I saw him in the list just now.
No, he's there in the list, Peter Weisz.
Yeah, I just now saw him.
Okay.
I don't know if he logged himself.
There and the microphone is on. His microphone seems to be on.
Oh, I see. Yeah, that's right. Would you say something, Professor Weisz?
there a problem with this microphone or something?
Okay, maybe. So what I can do?
Perhaps sending a message would be good, that we are not listening, in case he's speaking.
Okay, so maybe let me do something else while we try to contact him. Pushan's student, Saurabh, Saurabh, would you like to say something? I mean, some memories or some person, something?
Hello.
Hello, yeah.
Am I audible?
Yes, you are.
Yeah. First of all, I want to thank the organizer for this Pushan Majumdar Memorial Session for DAE Symposium. And I want to thank all the speakers for remembering Pushan through his works. And of course, along with the physics what Pushan did, all these speakers shared also their personal memory there with that. So I want to thank all of them for that. And I couldn't believe that shocking news on I got the news on 11th May morning, and I couldn't believe that. And I'm sure none of them could believe, because he was physically, he was such a fit person, and his demise is a personal loss for me. And I'm sure he will be missed by the entire physics community and his friends, by his friends and colleagues. And yeah, I just want to share one thing about him. That is about his very warm personality. Actually, that thing only get me going through my PhD, because everyone can know that his cheerful voice, and that his very warm nature and that cheerful voice just with many difficult times and difficult situations make them very easy. And that even happened after my PhD. Even in difficult times I used to call him, and things used to get more easier. And I want to convey my condolences to his family, friends, and colleagues. Yeah. Thank you.
Thank you, Saurabh.
Hi,
Yeah, hi.
I am Rini Gupta. I am his elder cousin sister.
Yes, ma'am, please go ahead.
I would like to thank you all for holding this meeting.
Oh, he was very dear to us.
So vibrant that I just have no words to say about him. He was lively, he was vibrant, and previously, definitely I didn't go through his works. Thank you all for letting us know about the volume of works he did. Thanks a lot.
Thank you very much for joining in and saying something. Okay, so I understand that Professor Weisz. Yes, please go ahead, Amol.
Message of Professor Weisz be read.
Okay. So I take it.
He's asked for you to read it, Shobin. He's written that in the chat box.
Yes. I read that. So I'll just go through it. He sent a mail saying, yeah. I first met Pushan in 2000. I was one of his PhD examiners. As you know, Pushan was a student in Chennai of Professor Sharat Chandra. with whom I had collaborated nearly 20 years earlier when Sharath came to DAISY as a postdoc in 1981. I was immediately impressed by Pushan's enthusiasm and bright aura, so a few years later, I strongly supported his application for a postdoc position at the Max Planck Institute in Munich. We discussed a lot, but I didn't directly collaborate with him. He mainly worked with two other MPI postdocs, Yoshiaki and Miho Koma, on computing global masses using the multi-level algorithm. He finally wrote an article for Scolapedia in 2012, for which Pushan did most of the work. Pushan was a pleasure to have at the institute, always friendly and willing to help everyone he met. He was involved in organizing seminars and occasionally gave talks himself, and those who knew him well sat at the back of the room where his booming voice was dampened a bit. He was, as you all know, lover of sport of many kinds. He came to the institute by bike, was a keen and talented footballer, and organized MPI, Max Planck Institute, football games. After his leaving MPI, we kept close contact. When he traveled via Munich, he would visit me, and I also visited him in Munster and in Graz. In 2010, at an ISS meeting, Pushan invited me and my wife to stay at his apartment in Kolkata, and he and his wife Vasudha were very kind hosts. We kept sparse but regular email contact. In fact, on May 4th, he wrote a mail to me which showed no signs that he was not feeling well, and hence the news about his death came as a big shock to me. In that letter, he reported how he was working from home because of the pandemic. It's not too bad as I can access the computers as usual with an extra hop. He mentioned that his children, of whom he was very proud, were having online school lessons. He also wrote that the economic outlook in India was bad. The government has frozen our salaries for a year and a half and cutting all sorts of grants so that he couldn't attend the lattice meeting this year. He was a wonderful character, talented physicist, and a good friend who died much too young. So this was Professor White's message. Uh, Thank you very much for joining in, Professor White, in this session. Amol, you said you wanted to share something?
Yeah. So I was a postdoc with Pushan when he was at Max Planck. And of course, I do recall many of the instances that Professor Weisz just mentioned. The way to remember Pushan is through his various passions. And from what I found, some of his passions were, of course, trekking, as everyone said. He did take us to many mountain climbs in the Bavaria. He, of course, was very fond of cooking. And he was the one who tried to teach me the perfect recipe for Bengan Bhaja, which happens to be one of my favorite Bengali dishes. One thing that he used to get excited about, at least during those days, was when he managed to reduce the time for running of a program by a factor of 20%. And he would be so enthusiastic that he would come and say, yes, I did this. I managed to reduce the time of running by 20%. And he would try to explain to me how he did that by putting some comments on top, which of course were the one thing we did, which of course also what Professor Weisz mentioned too, was actually conjure up a ragtag um, team of football, which I perhaps I'm sharing here. And you will see Pushan standing here. Among this team, Pushan used to be the one who would run from the back end to the fore end of the field. All of us were newcomers. He held training sessions for us and was everywhere at the same time. We actually managed to hold football matches. This is just before or after a match that we held with Deutsche Luftraumfahrt, which is the equivalent of ISRO. We of course lost very badly because we were like playing 11 versus 1, and only one in our team was actually Pushan. All these small memories will stay in our minds, and I think that's how we will remember Pushan, and that's how he will live in our hearts. Thank you.
Thank you, Amol. May I request some of his IACS colleagues to say something? I mean, some of them said, I mean, he contacted them.
Shulman, if possible, can I just put in a word or two?
Yes, please. Yeah, go ahead.
Hi, everybody. It's a rather sad occasion for me because I never thought I would live to see this day. Pushan was not just a colleague, but a very dear friend. And I would just say two aspects of my interaction with him over this last 12 years or so when I moved to IACS. He was there a year before. The first thing that I noticed is that he had an amazing grasp of different branches of physics, and particularly if you could translate any problem in the language of mathematics, he had always something interesting to say. And this goes to his, I would say, encyclopedic knowledge about different branches of physics, and would frankly say that I haven't seen many people like him in this respect. Of late, he has started, sort of working in some aspects of condensed matter, and Arnav Sen was collaborating him with on this, and he'll probably say something regarding this. Also, he was a great help in terms of every kind of computing needs that one may have. And for me, being a person with almost zero knowledge of computers and how they work and stuff like that, having somebody like Pushan is really great. And I think our whole institute relied on him in terms of computing needs, something that Sourendu already said. The second point that I would like to bring up is that I was one of those, trekking buddies of Pushan, which essentially means that I was, the non-fit guy whom he would drag to high mountains. And these trips have really opened up my horizon in several aspects. But just to cut a long story short, here among the Himalayas, out of the confines of the city, you would see Pushan in his true elements. And I would like to remember him as a friend, and would always be there with us. Thank you.
Thank you, Krishnendu.
Hi, Soumen. This is Arnav Sen. Can I take a couple of minutes?
Yeah, sure. Go ahead.
So first of all, thanks for doing this session. This was a great idea. So I would just like to say a couple of things about Pushanda. We have heard a lot about him. So I joined IACS in late 2013, and I was very, very lucky to have Pushanda as a colleague from day one. And over the years, he became a dear friend, and he was invariably the first person I would go to whenever I needed any advice, because I just trusted him a lot. I deeply miss his warmth and ever helpful nature. And I also miss his detailed descriptions after coming back from his treks. And I just feel quite sad whenever I come to office now, because his office was just next to mine. So on the physics front, I benefited enormously from my numerous discussions with Pushanda. In fact, our shared passion in Monte Carlo algorithms led to some projects in condensed matter theory regarding probing topological excitations in spin systems. And this was a few months before his untimely demise. With his last student, Moinak Pal, who's now doing his PhD with me, I hope to finish some of these projects and imagine that Pushanda would be satisfied with the outcome as well. And lastly, we all miss you, Pushanda, and yeah, that's it. Thank you.
Soumen, can I say something now?
Yes, please. Yes, Saurabh.
Yes. Can you see the slide?
Yeah. Yes.
How to make it full screen. Let me see. Okay, if it is visible, then let me just. Let me share my memories of Pushan as a very dear friend and who was like my younger brother. Pushan and I met during the HEP school in Chandigarh in 1996. We became friends instantly, and that was the magic of Pushan. Those of you who knew Pushan know it very well. During a 2-day break, he took us to Shimla, and I learned how passionate he was about going to the Himalayas and looking at the snow peaks. Later on in the same year, in December, after the DA Symposium in Guwahati, we went to Bomdila in Arunachal Pradesh. That was a very exciting trip with Pushan. One day while walking, I suddenly slipped on the icy roads. Remember, it was end of December and Bomdila is at an altitude of about 9,000 feet. Pushan immediately caught hold of my arm and pulled me up. I survived. And literally, for the next 24 years, whenever I was in trouble, he came to my rescue. We were colleagues at ISCS for the last 13 years. Although we never collaborated, but I had numerous physics discussions with him on different topics. Here, I forgot to show it to you. Here is a photograph from HERC school in Chandigarh. You can see Pushan standing on the last row here. Okay, let me continue. So you are colleagues at ISCS for the last 13 years. Although we never collaborated, but I had numerous physics discussions with him on different topics. These discussions were always a great learning experience for me. Whenever I had any difficulty in understanding something, he helped me. We visited many places together. We attended BC Spin School in Kathmandu. Here is a picture from that BC Spin School. You can see Pushan listening to one of the lectures, sitting here. This is another picture from the same trip. We went to see the Annapurna Peak near Pokhara in Nepal. We visited many different countries in Europe. For example, here is a picture taken in Helsinki. He was visiting us in Helsinki. So this is also a picture in Helsinki, taken in Helsinki. This is one of the pictures taken during our visit to Keukenhof in Netherlands. Ashmita Mukherjee is also seen in this picture. We went to see the Aurora Borealis in the northern part of Finland beyond the Arctic Circle. This visit in particular would not have had happened without Pushan. He was the main driving force. Pushan came to Finland several times, and we went to Graz when he was there. Last December, we visited Puri with our families. Pushan treated us to a fantastic dinner and then dropped us off at our Hotel-Weisz car. Here you can see this picture of Pushan on the Arctic Circle. All of us know he was so passionate about playing football. We played football together at TIFR and also at ISCS. I still hear that voice, Saurabh, chalo khelte jai. Saurabh, let's play football. We could not complete that game of football, Pushan, but you and your love for physics, football, mountains, coffee making in our coffee club, and so many other things will always be there in the deepest core of my heart. My dear friend, goodbye.
Thanks, Saurabh, for these stories and showing this bunch of very interesting photos of Pushan. Yeah. Would anybody else from the audience like to say something? Since the topic of football was mentioned, let me put in a short story. I have had various interactions with Pushan research and ACRC school. He taught, I was tutored, I taught, he was tutor and all that. I went to him many times with problems with algorithm, problems with math. He often helped. Never took pride in it, except once we were playing this very amateur football in TIFR grounds, and he did something trick. I was completely fooled. At the end of the match, he beamed and said, "See how I fooled you." So that seemed to be the only time he thought he did something for which he can take pride. May I? Yeah.
Can I say something?
Yes, please.
On a lighter note, he went to Japan once for a symposium, and the only shopping he did from Japan was a football.
Okay.
That's him.
Yeah, he always, I mean, I have heard him brag about this Munich team, football team that he was running. I didn't realize that the other players are like Amol.
Yeah, he was very passionate about all he did.
Soumen, can I say something?
Yes, please.
On the football, I had, of course, also, this is Rajiv Gawai. I was in TIFR, right now I'm in Bielefeld. With Pushan, I also, of course, had a lot of discussions on football. And I always used to tease him that India as a footballing nation is really very low in the ranks. And his reply, which he gave, is with me. I have so far never found counter to that. He said, that's because we don't eat beef. If we ate all beef, then we'll all be strong and we would be able to play the football much better than we are really able to do. Coming back to the times that he actually joined us in TIFR as a postdoc, he was actually a fresh PhD from Chennai and had worked with Sharat Chandra. And the subject that he had worked on had practically nothing on the side of the numerical issues, was more mathematical. And so I was a little worried of how he will actually show. He was one of those extremely rare postdocs that we really find who actually was excellent in both analytical side as well as numerical side. And he actually joined us in the effort to develop the algorithm for dynamical fermions that we were at that time trying to do. Up to that point, that computers in India and of course in TIFR also were rather too small to actually allow us to do any fermionic simulations. And we together actually developed the hybrid algorithm, as it is called, and I still remember the discussions he used to have every day with me. I think what was really remarkable, and I still remember about those discussions, is that he really contributed in the best possible way as an equal partner. He was a young person who had practically no experience either on fermions or on the fermion algorithms, And yet, both in terms of his own preparation and his own thinking on it, he really made that thing work in a rather short time. And that's where we actually went on to use that for doing the dynamical susceptibility calculation. I think the overall impression that I have about him is that he really had very clear idea, meaning physical picture of what exactly these algorithms were. So that is why even in the context of this diffusion coefficient, the trick that he actually talked about improving was something that he really knew what exactly had to be done. And that is exactly where he contributed in a tremendous way for that. Of course, any discussion about Pushan would be incomplete without mountains. He was the one who actually, in discussions with me in Calcutta, persuaded us to go to Sikkim, and we then later on went to Sikkim, and he had given lots of hints of where to go and so on. And every year, whenever he went to mountains, he would send pictures of that and suggest that one should really go for it. It is really absolutely incredible that a person who was so uh, physically fit, lively, and active should actually succumb to this kind of what one would call as a absolute unexpected disease or shock. Uh, we all are saddened, but I too was really very, very shocked to hear that. I'm pretty sure he would have contributed a lot to the lattice as well as the computer scenario in India. His knowledge of the computers, both hardware and software, was really humongous. And I think that would be very strongly missed, as would be his insights into improving the speeds of the programs. So I think my sincere condolences to his family and colleagues, and of course, tribute to his work as well as spirit. Thank you.
Thank you, Rajiv. There's a message in the chat box from Tanushri Rai who says, Many here is a great scholar, but didn't know the magnitude and depth of his work. He is very dedicated both to his profession and to his family. His passing away is very untimely and very, very unfortunate. I think we all agree. Talking about his family, we are fortunate that some of his family members, his wife in particular, have also joined in. Thank you, ma'am. In case if you like to say anything at any point of time, please just stop me and go ahead. Okay. We have certainly.
Showman, can I take just a couple of minutes to say something? Rajdeep here.
Yeah, please go ahead.
Okay. Hi, I am Rajdeep Sen Sharma from TIFR, and I am, of course, not from exactly the same physics field as Pushan belonged to. I am a theoretical condensed matter physicist. But as Krishnendu said, I was one of his trek buddies, whom again he used to take on these various trips. So maybe a couple of very short stories. One thing that always amazed me about Pushanda was, of course, he had this great spirit, but underneath how organized he was in all of these trips. So I remember on the first trip, we were rearranging bags, and I saw he was carrying a huge rope, the kind of things that you tie, for example, boats and stuff with. And I said that we are going on a, this is a more or less an amateur trek. Why are you carrying this huge equipment like rope and stuff like that? And lo and behold, we came to a point where because of some snowfall, the path was completely frozen, and we had to take an alternate where we had to actually walk by essentially keeping ourselves at 45 degrees to the mountain slope. And of course, his rope came in handy. He did it without the rope, but for us lesser mortals, he had the rope, and that was one of the reasons we could get back in a reasonable amount of time with all of this. So every time I went with him, there was another time when we were going on a trek, and his trekking shoe came off. And he said, okay, fine. Then we went to the camp, and then he took out a very, he used to carry needles with which he can tie up his shoes when they're completely torn, so that he at least gets to come back and so on. So together with this indomitable spirit, this core organizing thing had always amazed me, that he had a solution for every contingency that we could face on a trek. So, and he would basically guide us essentially like a very senior elder statesman, guiding people who don't know what they're doing and so on. And we have, over the last years, gotten a little busy, and we have talked about many trips with none of them actually being organized. But surely the next time we go on any trip, we will miss this towering presence and his indomitable spirit. So condolences to his family, and just wanted to remember him for this very free-spirited and booming character he was. Thanks.
Thank you, Rajdeep. Well, we have any kind of exceeded our time, so if nobody else has anything to share, let us all thank again his family members for being here, and our collective condolences. It has been a great miss to us in the community, but you can only imagine what kind of a big loss it has been to you.
Thanks a lot.
Yeah. Yeah. Okay. That was some. Yeah. So let me. Yeah. Thank you again for staying this late for this session. Thank his family for being here with us, and thank all these Vedanga and the DAE committee and all these people who arranged this session. Thank you.
Thank you, Sunny. Thank you all.